Looks like Hollywood just can't make a space movie without messing something up, right? The movie Deep Impact, released in 1998, starts with the following scene. A group of people with amateur telescopes are conducting nighttime astronomical observations in the countryside near Richmond, Virginia. And the mistakes start literally in the second sentence spoken in the film. One of the people lists the stars they are observing, saying Altair, Alpha Centauri, and the small problem is that they just showed us where the observations are taking place. Richmond is in the northern hemisphere, far from the equator, and Alpha Centauri system simply isn't visible from there. It is visible from the southern hemisphere.
Alright, you might say that's a minor detail, and overall I agree. I'm usually not the one to nitpick errors in movies, especially if those inaccuracies serve the plot.
But a mistake like this with the star seems completely unnecessary. Yes, most of the people won't even notice it, but just to name a different star and that's it. But this is only the beginning. A man, apparently a teacher, approaches Elijah Wood's character, glances up at the sky, and asks, "What's it called?" He replies, "That's Mizar, a double star. And next to it is Alcor." It's unclear how the man knew exactly where the telescope was pointed with such precision, but what happens next is what matters. Elijah Wood's character sees an object in the telescope that he can't identify. The surprised teacher looks through the telescope, and then there is a bit more movie magic. Elijah tells him to look 10 degrees south. 10 degrees in the sky is equivalent to 20 full moons. And the man just finds the object without moving the telescope at all. Given the telescope that was shown, the type of camera in the telescope, such a wide field of view shouldn't be possible. Someone might say it's just the first 2 minutes of the movie and there's already so much nonsense. But most viewers didn't even notice it. Perhaps there were some people who noticed these mistakes and shrugged them off, thinking, well, it's just minor stuff.
But then, in the movie, real fun begins. And I think this can even spill into the real world and affect how people react to news about asteroids.
Basically, the strange unknown object is photographed and the image is sent to an astronomer at an observatory. He, while eating pizza, enters the object's coordinates in the sky and points a large scientific telescope at it. He sees the object on the screen and it turns out to be a comet. What does he do next? Of course, he quickly calculates the trajectory of the comet and, oh no, the pizza slips from his hands. The comet is enormous and it will inevitably collide with Earth. And of course, everything we've seen in this part of the movie is complete nonsense as well. He received just one image of the comet, and all that image would confirm in reality is that the object exists. Magically calculating the trajectory of an object based on a single observation and with such precision that the astronomer in the film was completely confident that it would collide with Earth is impossible. I'm not saying it's the fault of this film, but perhaps it, along with others like Armageddon, which also came out that year, has made some contribution to the standard perception of the average person about how the detection of new asteroids and comets works, as well as determining the chance of their collision with Earth. Here, the scientists have just discovered the object, and they already know for sure whether it will collide with Earth and when. And now, several times a year, news about another killer asteroid appears in the media. And there are always people who are worried by these reports.
Instead, we should be I mean, so far, in 100% of cases, those news reports turn out to be exaggerated.
Sometimes they talk about an imminent collision, but in reality the chances are in the tens of thousands or even millions to 1. But how can the orbit of a distant object actually be determined? And how can we calculate the chances of it colliding with Earth? This is one of those tasks that might seem impossible to the regular person. Similar to how some people think that it's impossible to know what's inside a distant planet. How can you determine the actual trajectory of an object in space based on a faint dot in the sky, and even calculate whether it will collide with Earth? But just like with the interiors of planets, there are clever ways to find this out. Moreover, with varying degrees of success, scientists have been doing this for hundreds of years. So, how do astronomers do that in reality, not in the movies? How successful are they at this? Can we avoid the planet-killer asteroid?
We'll discuss all this and more today. My name is Andrei, and this is Cosmos Elementary.
So we've discovered a new object that could be an asteroid or a comet. And of course, we want to learn about its properties and calculate its trajectory. By the way, regarding the discovery, usually with just one image, as shown in Deep Impact, not only you can't calculate the trajectory, but you can't even discover the object. The process of discovery shown in the film is very unrealistic today. In the very first shot, we see a detailed image of the comet with a coma, and its hazy appearance clearly indicates that it's not just some background star. But in reality, things are quite different. At the time of the discovery, the object is usually still quite far away and appears only as a point, sometimes barely visible. To understand that it's not a star but a previously unknown object in the solar system, you need at least 2 images of the same area showing that the object has moved relative to the background stars. That's, for instance, how Pluto was discovered. Back then, images had to be reviewed manually, and modern technology eliminates that need. Automated systems photograph the sky and track whether there are objects moving relative to the stars that aren't in the databases of known objects. But once we've found an object, we need to determine its orbit or trajectory. How do we do that? I've already said that a single observation is insufficient for determining an orbit. You need at least 3, and the more, the better. There are several methods for determining orbits. But let's first look at this question naively to understand how difficult it actually is. We are conducting observations of a comet from Earth. Even if we have several observations taken at different times and we see the movement of the comet, we are only seeing a projection of that movement on our celestial sphere. The stars serve as a background, remaining nearly motionless over long periods. Although of course they do change position over time, it is so slow that when assessing the movement of the solar system objects, in most cases this can be ignored. So we see the night sky as if it were the surface of a 2-dimensional sphere in which we are located, and the comet moves across this sphere. How do we determine the actual motion of the comet in 3-dimensional space from this? To intuitively grasp that this is at least theoretically possible, it's clear that we're missing some key information. So we have 3 images of the comet taken at different times. It would be helpful to also know the distance from Earth to the comet during those observations. Then the 2-dimensional projection in the sky can be transformed into the actual position in the solar system at those 3 moments. Can we determine that distance? Well, in principle we can, although the situations can vary. For example, if the object is close enough to Earth, we can use radar measurements. Send a radio signal to the object, and if it reflects back, by measuring the time it takes for the signal to travel to the object and back, and knowing the speed of light, we can calculate the distance. The issue is that this method isn't always available. Another method is the parallax method. I discussed it in detail in my old video about measuring the distance to the Sun. In this case, if we observe the same object at the same time from different locations, its position in the sky will differ from those 2 points.
It's like in the famous example with the finger. I do like this, then I close one eye, then another one, and I see how the position of the finger changes relative to the background.
I found an example of a student project where they tried to determine the distance to comet Hyakutake. Here are 2 images taken at the same time from Denmark and Portugal, and we can see that the position of the comet differs. Next, a bit of trigonometry allows us to estimate the distance to the comet. Naturally, a simple calculation will have a significant margin of error, but we can get a rough estimate. And continuing with our naive reasoning, we now have 3 points in the solar system where the comet was located at 3 different times. Next, we can draw an arc through them, and bam, as if we already have a piece of the orbit. If we make more observations and measurements at different times, we'll have more points and more accurate orbit. And if, for example, we have an asteroid on a shorter orbit and we can track the entire orbit, that's ideal. Additionally, we can estimate the distance based on changes in the asteroid's observed brightness. But let me remind and emphasize, this was just our naive assumption of how it could theoretically be done. We are overlooking many important details. In some cases, something like this can indeed be pulled off, but not always. Of course, we also need to consider the position of Earth and its movement within the solar system. This greatly affects how we see an object, and because of this, it doesn't just move along an arc, but along a curve that can even start moving in the opposite direction, what we call retrograde motion. For example, this is the trajectory of Mars in the sky. There's also the rotation of Earth on its axis and where on Earth the observation was made. However, distance estimates, for example, can be very inaccurate. Even small changes can significantly affect the calculation of an orbit. But in reality, it is indeed possible to calculate the orbit of an object without directly being able to measure the distance. So, assuming we can accurately determine the distance and observe an object for a long enough time, especially with modern technology like computers that can quickly perform calculations and build models, it starts to seem like it's not such a difficult task after all.
Well, first of all, just because it seems that way, it doesn't mean that it is true. And secondly, we haven't always had those capabilities.
I already mentioned that orbits have been calculated for hundreds of years. Back in the times of Gauss and Newton, there were no computers. And if an ordinary person not involved in mathematics and orbital mechanics looks at examples of such calculations, they would say, "What?" By the way, why is it difficult to calculate the orbits of comets specifically? We've known the orbits of major planets in the solar system quite accurately for a long time. We've been observing these objects for thousands of years. In fact, attempts to explain their motion across the sky ultimately led to the development of the correct model of the solar system, rather than the one where Earth is at the center and planets require all sorts of fixes in the form of epicycles and similar things. Additionally, the planets do have relatively circular orbits. We'll discuss this further later. But in the case of a newly discovered object, we don't have the luxury of decades or even centuries of observations. This is especially true for long-period comets that have come from the depths of the solar system, or even for interstellar objects. Here, the term observational arc is used. It refers to the trajectory of the body across the sky from the first to the last available observation. Usually when I delve into a topic with a long history, I try to provide at least a brief historical overview. And I usually talk a little about how our understanding of something has evolved over time in chronological order. But today we'll do things differently. First, I'll show an example of how this can be done today, and then we'll look back at the past to see how it was done back then. We won't dive deeply into the mathematics, but we will at least gain an understanding of how challenging it is. So let's assume we have discovered a comet, and so far we only have a limited number of observations. However, there is an opportunity to continue these observations in the future. Kepler, even before Newton and his theory of gravitation, claimed that the motion of an object is determined solely by its orbit, and that the orbit itself can be described by a series of parameters. These parameters are known as the orbital elements. They describe the size, shape, and orientation of the orbit. Orbits are considered as conic sections, and let me briefly remind you of the main elements. The shape of the orbit is described by a parameter known as eccentricity, which indicates how elongated the orbit is. A value of 0 represents a perfect circle, though in practice such orbits do not exist. A value of 1 represents a parabola, while values greater than 1 correspond to hyperbolas. Values between 0 and 1 indicate ellipses. And all objects orbiting the Sun move along elliptical orbits. The eccentricity for different objects falls within the range of 0 to 1. The size of the orbit is described by the parameter known as semi-major axis. This is the distance from the center of an ellipse to one of its ends. There's also the inclination, which indicates how tilted the orbit of an object is relative to the plane of the ecliptic in the solar system. The three remaining classical elements are the argument of periapsis, the longitude of the ascending node, and the true anomaly. In general, if we know these elements, we know the orbit. But that's exactly what we're trying to determine. It feels like we're stuck here. So, what do? We guess.
And you're like, what? And all the conspiracy theories that claim that all of the scientists are always lying say, aha, but don't jump to conclusions just yet.
Of course, if we randomly select not just one but several parameters, each with its own value, we will never get it right on the first try. First of all, we don't have to guess completely blindly. From the observations we already have, we can at least vaguely constrain some parameters. But the main point is that we have these guys. First, we select parameters for a specific moment in time, say during one of the observations we have. If we have chosen the parameters, then we can construct a model of the orbit. We have a proposed orbit, and we can virtually move our comet along it. The most important thing this allows us to do is predict where on the celestial sphere the comet will be at a later moment in time. Of course, we also need to remember to account for Earth's movement in its orbit and its rotation. Let's say that this is our available observation, and we know where the comet was in the sky at that moment in time. Our model, based on arbitrary values, predicts an arc like this. I chose this shape just for clarity, and this model predicts that after some time, the comet will be here. Next, we need to conduct observations or use existing images taken later. Given that we initially selected the values quite arbitrarily, it's likely that the predicted position of the comet in the sky will be far from the actual one. We predicted it would be here, but in reality, it turned out to be over here. But this is just the beginning. Now we can start making small adjustments to the value of each orbital parameter. And next time, perhaps, our predicted trajectory will be closer to the actual position. Of course, these are very simplified illustrations that I've myself made. In reality, this requires a lot of calculations, but as I mentioned, today we have computers that greatly assist us with that. In an article on the European Space Agency's website, which I used as one of my sources, this process is referred to as parametric optimization, and each step is called an iteration. The more iterations we perform, the closer the predicted position of the comet in our models will be to its actual position in the obtained images. There will eventually come a moment when further improvements will no longer be possible, and the predictions of the model will align with the actual trajectory. But of course, this is not the end. First of all, our observations are not perfect either. Again, we're talking about a comet. It may exhibit a comma, making the object appear fuzzy, and we might not accurately know the position of the comet's nucleus in the image. A couple of pixels or angular minutes and seconds off here and there can result in a significant difference from the actual position and introduce inaccuracies into our results. Much, of course, depends on the duration over which we have observations. If we have few images, a short time period, and the comet has a long orbital period, then inaccuracies can be substantial. The obvious solution is to have more observations. The more observations we have, the more accurately we will know the orbit. Additionally, once we have determined the orbit with a certain degree of accuracy, we can dig through archived observations from various telescopes and find images of our discovered object. It is quite possible that it has already been within the field of view of telescopes before, but it was not recognized. In that case, we will have even more observations. It should already be clear how absurd the scene from Deep Impact is, especially considering the instantaneous calculation of a precise collision with Earth. The very fact of it, along with the timing of the impact, is quite unrealistic. In practice, when we have determined the orbit with a certain degree of accuracy, we can check whether it intersects with Earth's orbit. Additionally, since we know where Earth is located on its orbit at any given time, we can also see if the trajectory of our comet or asteroid intersects with Earth itself. While the accuracy is still low, there are various possible orbits that might fit, leading to low precision in predicting a potential collision with Earth. It is possible that shortly after the discovery, the chance of a collision may appear higher because there are still many uncertainties in the orbit. That's why we should approach news about yet another killer asteroid with particular skepticism, especially if it has just been discovered. We need to wait, sometimes a considerable amount of time, for astronomers to conduct more observations, perform more iterations, and refine the orbit. And typically, as the orbit is refined, the likelihood of a collision decreases, assuming the object turns out to be potentially hazardous at all. Of course, today there are various methods for determining orbits, but in general we can conclude that the availability of modern telescopes and surveys, computers, and the ability to quickly perform complex calculations in large quantities, build models, allows us to calculate the orbit of a new object with a certain degree of accuracy and assess the likelihood of its collision with Earth.
But none of today's capabilities would exist without great scientists and mathematicians of the past, such as Kepler, Newton, Lambert, Halley, Gauss, and many others.
Kepler observed comets but did not fully understand their dynamics. He considered them to be interstellar objects. However, he developed his famous laws, without which determining properties of orbits would be problematic. Newton built upon Kepler's work, developing his laws of gravitation. He calculated the orbit of the Great Comet of 1680. Soon after, Edmund Halley, using Newton's work, was able to predict the return of the comet that we now know as Halley's Comet, which returns to the Sun approximately every 76 years. But also, I wanted to illustrate how complicated this process was a long time ago, using the example of Carl Friedrich Gauss, although the calculations were for the orbit of the dwarf planet Ceres. That's what we call it now, and also we have images taken from close range by the Dawn spacecraft, while the situation back then was quite different. In 1789, William Herschel discovered the planet Uranus. Initially he thought it was a comet or a star, and it was only accepted as a planet 2 years later. It turned out that Uranus followed the Titius-Bode law, which predicts that each successive planet in the solar system is approximately twice as far from the Sun as the previous one. However, the error can range from 25 to 50% of the predicted position according to this rule. And for the first 7 planets, this rule worked quite well. Here is a graph where the predicted distances are shown in red and the actual distances are in blue. We see that the rule starts to break down at Neptune. However, when this rule was established, no object was known in between the orbits of Jupiter and Mars. Its existence seemed almost inevitable. In 1800, astronomers aimed to find it. On January 1st, 1801, the Italian astronomer Giuseppe Piazzi from his observatory in Palermo discovered a new object, which he named Ceres. The astronomer was able to observe this object for only 41 days, obtaining an observation arc of 9 degrees, after which the object disappeared behind the Sun and was lost. After some time, it was expected that it would reappear, and astronomers wanted to attempt to find Ceres again. For this, they needed to calculate its trajectory based only on Piazzi's observations. This added complexity to the task as they couldn't obtain new observations. Uranus, after its discovery, could be observed further. And again, in the case of Uranus, astronomers made the assumption that its orbit was circular, which was close to the truth. For Ceres, the eccentricity could range widely between 0 and 1. Many great minds of that time attempted to solve the problem, but they were unsuccessful. Laplace, for example, considered it unsolvable given the conditions and available data. But Carl Friedrich Gauss thought otherwise. Using his own method, he was able to calculate the orbit of Ceres. And with Gauss's ephemerides, astronomers were able to locate the object again. I found an entire book that describes in great detail how Gauss managed to do this while working with limited data. In total, Gauss, and everyone else, had data from 22 observations made over the course of 41 days. There was information about the object's position on the celestial sphere, including its coordinates and the exact moment when the observations were made, down to fractions of a second. However, the calculations took about 100 hours. Gauss's strategy was to first determine an approximate orbit and then refine it to make it more accurate. Initially, he worked with 3 observations. As I mentioned, we won't go into the full method, but we'll at least try to understand the complexity of the task. What did Piazzi observations provide? The position of the Earth at the moment of the observation, and more specifically the position of the observatory at that moment, as well as the position of the object on the celestial sphere. As I mentioned earlier, if we know the distance to an object, it becomes more realistic to determine its orbit. But back then, of course, there were no radars and no observations from which parallax data could be extracted either. There was only what Piazzi had obtained. So we take 3 observations from the 22. From the observation points marked E1, E2 and E3, we can mentally draw a line from these points to the object against the background of stars, extending into infinity. Somewhere along these lines is the real position of Ceres in space at the moment of observation. These points are marked as P1, P2 and P3, but they are indicated here arbitrarily. If we know exactly where in the line this point is, we know the distance, but it could be anywhere. Well, almost, within the solar system with certain constraints. Gauss first set the task of finding the distance to one of the points, and then worked from there. In a system where the center of the Sun is marked, along with the positions of Earth at the time of observations, and where these lines exist, we can start applying geometry. Laying out a plane incline relative to the ecliptic in which the orbit lies, drawing triangles and parallelograms, calculating angles and using relationships from Kepler's laws. Each step in Gauss's calculation process gradually eliminated another unknown, and eventually he managed to calculate the distance and ultimately determine the orbit. Today this process is known as Gauss's method. There are others as well, such as Lambert's method. Subsequently, the method was refined, and as we've already established, no one today spends dozens of hours with a pencil and paper trying to determine distances. Most of the work is done by computers. Returning to the threat of a collision between an object from space, such as a comet or an asteroid, with Earth. Today there are several systems, one of whose primary tasks is to observe the sky for new potentially dangerous objects. For these objects, after the discovery, an approximate orbit is first determined and then refined. These are surveys like Pan-STARRS, MATLAS, NEOSM and others. The surveys are spread across the globe and observe almost the entire sky. There are databases of potentially hazardous objects where you can check an object from the news yourself, its actual probability of colliding with Earth. These systems are able to predict objects that actually enter Earth's atmosphere, but still, the majority remain undiscovered until collision. Because, as a rule, these are small bodies. It's difficult to detect them in advance. The prime example is the Chelyabinsk meteor. But they can certainly cause damage, although not like the so-called planet-killer asteroids the media talks about. Truly large collisions happen very rarely. Sometimes you might even hear the opinion that all of the large potentially hazardous near-Earth objects that could cause global catastrophes and extinction events have already been discovered. We should have already found all large, close and bright objects.
Never say never.
And something can always come in from the outskirts of the solar system or from the region where objects are hidden by the sun and its bright light. We can only hope that constantly improving monitoring systems will allow us to detect a sufficiently large object in advance, so that measures can be taken. Asteroid deflection systems are already being tested as well. Remember the success of the DART mission. And we must not forget that all of this would not have been possible without the great minds of the past. Still, in real life, everything is much more complicated than in movies. But when it comes to space, it's also much more interesting.
Thanks for watching. Links to all of the sources are, as always, down below in the description. And if you enjoyed this video, subscribe for more videos in future. I usually upload every 2 weeks. Bye.